last talk for today, and then it's a raffle. So my name is Josip. I work for a company called Sofascore, and I'm just going to ask one question, and then I promise no more. Can I get a show of hands of how many of you have heard of Sofascore? OK. Great. So basically, it's a sports platform that allows people to track live results, live scores. We have a lot of statistics. We have more than 20 different sports. It's a free app, which is important because then you have to really optimize your infrastructure. And we are global, so we have users all around the world, and the app never sleeps. This is a screenshot from the app, and I'm only showing you this so that you can see that we have a lot of different data and a lot of data points, and we aggregate a lot of different sources and then show that to the users. Our monthly numbers are this. So we have more than 28 million monthly active users. We have 1.4 petabytes of traffic every month. We have more than 400 billion requests that are hitting the service, and the peak was 1.6 million requests per second. So when we first started, we started with nothing, so it was 0 users. And those 0 users started to kind of get on the site, so we got more and more. And it was only on one shared server, and that was many, many moons ago. And when we started, we really didn't know what we were doing. So when a lot of people came online, and by a lot, I mean like 400 people, the site would crash because it was just not fast enough. And that's not really a way you want to be running your business. So when it gets popular, everything crashes. And the thing is, like, our baseline was really low. And then you get one really big game that's really popular, and then everybody comes online, and the site crashes. And only those who are most persistent would actually get to see the results because everybody else gave up. So you don't want to do that. So the first thing that we are taught what you should do is just to add cache. So that's what we did. We added cache, we added memcache, and it was a full-page cache. So we were just caching the content from the website, the whole HTML. We would just put it to the memcache, and then on the next request, if it's in the cache, we would pull it back. But the problem with this is, since the way the cache works, the pass-through cache, the way it works is, if it's not in the cache, then go on the back end, calculate it, save it to the cache, and then the next request will get that cache. But if it's not in the cache, and you have a big influx of users, what happens is all of those requests will go to the backend. So the same request will go to the backend, will get calculated thousands of times, and then maybe if the server didn't crash, it will get saved to the database. But usually what happens in this case is your database dies, or your backend service. Because while everything is in the cache, it's OK. The second it's not, it will die. And this is called a cache stampede problem. So we solved this in the early days by learning how our users use the app. So everybody wants to see the games that are currently being played. It makes sense. So what we did was we created a worker that would basically pre-calculate everything, so all the games plus minus 2 hours, and then proactively put it in the cache before it's actually expired. And this is called proactive caching. And this is what all of the big companies do. So when you open your Facebook, Instagram, whatever, it's not calculating that on the fly. So it's already prepared for you, and then you can just use it. So it's really important. It's really important to know how your users interact with the app, with the system, because then you know how to build out your system better so that it's more optimal. And now we have this interesting thing. So it's a story time. 15 minutes before a game starts, we will have a certain number of users. And in those 15 minutes, the number of users will usually triple or even quadruple. So we'll get a really large influx of users. And there was this big thing happening called El Clásico. For those of you who don't follow sports, that's when Real Madrid and Barcelona play against each other. It's the biggest event in the football on the world. And 15 minutes before that game, our server was, the CPU was through the roof. So we have 15 minutes to fix the problem, but we cannot fix the problem because we are not on the cloud, because this was like 13 years ago. And there's not much you can do. And then we are looking at the graphs and seeing, OK, so this is going to die. This is the biggest event of the year. We are not going to make any money. The users will get really angry, and how can we solve this? And then we were thinking, is there a way that we can survive this? And we are talking about just one match, so just one URL on the website. And we got to thinking and figured out that Apache, the server we were using at the time, is much, much faster in serving static content than PHP is in calculating the results. We are using PHP, by the way, yeah. I mean, Facebook is using PHP, so we can use it as well. And then we got to thinking, like, it would be amazing if this one URL was actually a static page, because then there would be no load at all. Because when you use PHP or any other language for that matter, even if you have cache, you still have to boot your app. It still has to go through all of the things that your app does to retrieve something from the cache and then display it to the user, which is slow. So we said, but I mean, it can be a static content, because we opened the website, we clicked on File, Save As. We saved it as elclasico.html. We uploaded via FTP, because you were using FTP at that point in time. And we wrote a rule that said, if the user goes to El Clásico, then just return the static content. And it worked. That's how you scale. Thank you very much. But I mean, there was an obvious problem, because it's a static content. It doesn't update. So what we ended up doing is we were watching the game, and then when a goal happens, we would just edit the file manually. We would 0 and put 1, and then upload via FTP, and then it worked. But it works. It works. So basically, that got me to thinking, this is obviously a use case for the cloud. This was 2012, 2013, and we need to go to the cloud. So I went to the founders and I said, we have this use case that's perfect for the cloud. Most of the time, our baseline is really low, and then we have a really big peak when we want to scale, and then when it goes away, we just want to scale down. And they said, sure, fine, OK, do you know how to do it? And I was like, sure, of course. I'm just going to Google it. Because we were young, I was in college at that point in time, everything seemed like it was solvable. And the only game in town at that point was AWS. So that's what we decided to go with. And going back on that story where we had a static file, I knew that we have to find some way to have that functionality, to have that speed, so that we don't have to load PHP and fetch something from the cache. I want to have something that's faster. And we found something called Varnish. If you're going to remember anything from this talk, this is it. So Varnish is a reverse HTTP proxy that caches your content. It can cache anything from HTML, JSON, whatever. If it's HTTP, it will cache it. It's free, it's open source, it's fast. It's what allows us to have the system that we have. I cannot stress how good this thing is. So it also has request coalescing built in, which basically solves the thundering herd problem. When you have a lot of requests for the same thing, it will only allow one request to go to your backend. Every other request will wait for the same content, obviously. And then when the content is calculated, it will get stored in the cache, and all of the users will get the same thing. Pretty amazing. So the setup was pretty simple. We had an Amazon machine image, which had everything baked in together with Varnish. We had a database, a couple of workers. We got rid of memcache because it wasn't needed anymore. And the reason why we could do this pretty easily to move to the cloud, and to have an auto-scaling group is because we were stateless. So I mean, this goes without saying you should be stateless wherever possible because scaling state is really difficult. This is something you have to keep in mind when you're building out new applications. And we also wanted to experiment with new technologies because we are engineers and we all love shiny new things, right? So I found Mongo, because web scale. And it worked great for a time. And then we started seeing issues like replication issues, where it's just broke and you didn't know that it was broken. We got data type errors where an integer is not the same as a long integer, and then it doesn't work. It was difficult to analyze data, which is a shame because that's what we do. Locking was, that was not a, we had some issues with locking because at that time, MongoDB, when you do updates, it would lock the entire collection and then nothing would work. And that's basically what we do all the time. We update the same collection over and over again because you have a lot of different games that happen at the same time. And also no foreign keys, which is, again, a shame because you want to have that consistency in this type of the application. So we figured out we made a huge mistake, and we want to go back to a relational database. And we found Postgres. And this is what we are using now. And I'm going to briefly go into why. It's open source. All of our stack is open source. It has advanced SQL capabilities, which is important to us. It has minimal locking. It has this really cool thing called multi-version concurrency control. It can be a whole talk on itself, but basically what it allows you to do is to update and read at the same time, which is really important to us. And also has great performance. Now, when I say great performance, people use, yeah, but it's a relational database. You cannot run a huge site on it. I mean, we're using this, so it has really great performance. We can do 1 million queries per second, and we can do 90,000 transactions per second, and one transaction, when you benchmark, right? So one transaction is actually 5 things that change the state. So basically, we do 500,000 changes a second. So it can take quite a lot. And if you want to do NoSQL, Postgres can also do NoSQL, probably faster than MongoDB. But to change, in my mind, it was something like this. So the app itself is global, so there's no time for downtime. And in my mind, it was like, we want to change the tires while going 80 miles an hour on the highway. But again, we were young, crazy, and it was like, sure, we can do it. What can possibly go wrong? Spoiler alert, everything was great, which now that I think about that time, it was crazy that everything went smoothly. Basically, what we did is we timestamped all of the data and then synchronized the changes from MongoDB to Postgres. And then when the synchronization was done, we just did it again and again until the window of changes was non-existent. And then we just switched, and it worked. So we lost the simplicity of Mongo because MongoDB is really simple. But what we gained was far more important. So we gained stability, foreign keys, and analytical power. And I think it's really important to recognize the right tool for the job and change if necessary. If you keep sticking to the wrong technology, the more you postpone changing, the more problems you might have. And I usually get asked, like, do you guys do microservices? So the app itself started as a monolith, and it still is, mostly. So what we did is we started to separate parts of the system that had different requirements, and we solved that way. But like when I think about microservices, and usually people want to try microservices on a new project, in my mind it's something like this. So you want to do something that's for Google scale, and you don't even have your first user. Probably shouldn't do that on the first run. What you should always do right from the start is asynchronous communication, and that's what we first started doing. Asynchronous communication is basically queues. So if you have something that doesn't need to be done right away, you just put it to a queue. And then you have workers, which basically take jobs from the queue and process it. It's something that was invented 30 years ago, and usually we collectively forgot that it works really well. We use beanstalkd, but any queue works. You should always queue everything that is slow. Even if you're using microservices, you shouldn't just call things synchronously if you can help it. Now, the system I described that was on AWS scaled with the number of users. But with scaling comes a problem. So Varnish was baked in to the image itself, which meant when we scaled the machine, new machines had empty cache, and also every cache was on its own. So the more machines you have, the worse the cache is, because you have more requests going to your backend servers, because every cache is by itself. So to solve this, it's not really rocket science. You just want to put your cache in front of your backend servers, not have them baked in. But I really want to optimize stuff. And if you see here, you also have to do a couple of requests. So if you have 2 varnishes, then you will always have 2 requests to the backend for the same thing. If you have more, then you have more. And that's not really what we want to do, right? So the way to solve this is just add sharding. So you hash the URL, and depending on the URL, you go to a different node. And this works really well because then you can scale your cache linearly. We took this even a step further, and this is what we have. So we have the first layer, which caches whatever is the most popular, and it needs to have a lot of CPU and a lot of bandwidth. But then you cannot have everything in the cache when you load balance. And then that layer shards to the next layer, which is basically used to keep everything in the cache. And if you do this, you can literally cache everything. Our cache hit rate is 99.5%, which means that we need, so 99% would be we need 100 times less. 99.5 would mean we need 200 times less capacity because everything is in the cache. But cache invalidation is hard. It's really hard. Because you can add cache and just put a TTL, but then if your TTL is small, it doesn't really help you. So what we do is, for things that actually change often, we have a TTL of 1 week. But we know when something changes, so we invalidate that, even if it changes every second. We actually do 50,000 to 100,000 purges every minute. And that's what allows us to have the cache that's so great. And also, people usually don't know how cache control header works. Usually, we all know the max age header. And the HTTP standard itself was pretty well defined. So Varnish knows how to read this. All of the CDN knows how to read this, and they also probably respect it. So if you do max age, that's how long in seconds your end client will store for. So your Android, iOS apps, browsers, whatever. Max age is how long any intermediate cache will store it for. So basically, you can say, I want to store this for 5 minutes, but I want the device itself to store it for 1 minute. And then refetch and revalidate. And there are really 2 really cool ones. So you have stale while revalidate. For example, if you have some endpoint that's really slow, let's say 10 seconds, you can say it's fine to serve the stale content on this, even if it's no longer fresh, but then fetch it in the background. And the effect you have is people will fetch the content constantly, everything will work, and then once the cache is no longer valid, it will just fetch the new result from the background, but your users will still get the old content, and it will be fast. An even cooler one is stale if error, which basically means if the backend is unhealthy, just return the last content that you have, even if it's no longer fresh. Because some content, usually, most of the time, is better than no content. So you basically get always online experience with this. So AWS was great. Cloud is great. I love the cloud. But the thing is, it's really expensive. So we got to a point where our data, so the egress fees, were costing more than compute. And like, I cannot live with this. So if you pay more for the traffic than you do for the actual work that's important, then something's not right. So we started thinking how to solve this. And the thing is, since our caching layer is actually separate from the backend services, we figured we can just move all of the caching servers away from the cloud, because when you rent out bare metal machines, usually the traffic is either extremely cheap or non-existent, so free. So that's what we did. We took our varnishes and just put them on dedicated machines, and we rent those out month by month. And everything else is the same. So it points to the cloud. Everything works. We got a 10x reduction in price in our network fees, because the caching hit rate at that point in time was 90%, so only 10% of the traffic actually had to go from the cloud. And then I got to thinking, what if we moved everything from the cloud? I did a back-of-the-napkin calculations to quickly see what the price would be, and I got to the conclusion that if we over-provision the system by a double, we will still see a price reduction of 4 to 5 times, which was a lot. So we migrated everything from the cloud. We went to bare metal, and the reason why we could do this is because our graphs of cache misses were looking like this. So the cache, if you cache correctly, you get to a point where all of the peaks are drowned just by your cache. So you have a peak, but like 90% of the people go for 10% of the content. So even if you have more users, they will probably hit the cache. So you don't actually have to compute that. And currently, like the system, the oscillations that we have is our baseline and our peaks in the cache misses are differentiated by a factor of 2. So in baseline, we have 100,000 per minute, and on peaks, we have 200,000. So we have a system that just can handle the maximum capacity, and that's it. And the result of this is cost of everything needed for production over time. So all of the clouds, all of the services, all of the infrastructure, all of the licenses, everything. So everything that we need to run the production. And this is over time. So over time, it got down. And now, this might seem like a lot. Doesn't look all that impressive. But if you overlay that with the number of users in the green, which grew, now you can see a bigger difference. So our users grew, but our monthly bill kept getting smaller. And that's also one thing. So when you make a mistake on bare metal, you're offline. When you make a mistake on the cloud, you can get a really nice bill. So this is a real screenshot from a company I'm not going to name because a friend of mine works there. So one of the developers made a mistake on a Lambda function. And in a day and a half, they went from 300K a month to 1.6 million in a monthly bill. And that's just life, you know. So you have to choose. Do you want to be online and pay for it a lot, or maybe be offline for 1 hour until you realize that one developer made a mistake and then reword it? Now, this is not for everybody. So I'm not advocating that you go off the cloud. But at a certain point in time, maybe for some of you, that will make sense. And the thing with bare metal is we have a lot of spare RAM, because you buy machines that are basically built the way they are. We use PHP, which uses very little memory, so we have a lot of RAM for cache. And we actually have more than 1 terabyte of RAM dedicated to cache just because we have it. It's free for us, which is a cool thing to have. And then usually people ask, yeah, but you know, when you're not on the cloud, you have the cost of people. People also cost money, and you have to have more people to manage that, which might be true. But the thing is, up until 3.5 years ago, so for the first 10 years of the company, we had only one guy doing everything for infrastructure. That was me. I mean, I didn't have a problem with it, but the buzz factor is 1. So if I go away, the company is basically dead. Now we have a DevOps team. And the DevOps team is 4 people. And they're actually from the backend side, and they do this part-time. So you can actually do it without the cloud and not need as many people. We also have a really interesting use case. So this is the number of requests over time. And you can see 2 really big peaks. And those 2 really big peaks are the first and the second half for a football match that's really popular. So we send out a lot of push notifications really, really fast. And people who follow sports are usually sport fanatics, so they will immediately open their app, click on the push notification, and see the result. And this happens in 2 waves. And if you heard the talk before mine, this looks like a DDoS attack. And it was detected as one by Cloudflare. And it blocked our users. And it was really difficult to explain to their support that this is normal for us, to a point where I had to float to the US to go to their headquarters and say, look, like, this is something that happens. This is normal for us. And when talking with their engineer, the guy was like, oh, yeah, that's a DDoS. Like, we obviously detect that as a DDoS. And I said, but this is normal for us. Yeah, I know. I'm just going to put an if. So if Sofascore, then don't do DDoS as much. I think that code is still there, probably somewhere. But like, this is important. You have to have good monitoring. Application performance monitoring is really important. This is a screenshot from New Relic, but like any Works, Datadog, any of the others. The cool thing you can have, if you have really good monitoring, you can see which of your endpoints use up the most time. So it's not about what is the slowest or what's with the highest throughput. It's actually when you combine those 2. So the thing that uses the most CPU time. And then optimizations can have really big impacts. So this is one optimization that we did. It was a stupid bug that kept loading things that it didn't have to do. And you get your latency down, which means your infrastructure costs less. It's easier to maintain. And your users get their data faster, which means that you're better than your competition. But sometimes you cannot optimize. It's already the most optimal version of the code that there is. In that case, usually, you can increase the cache. And so it's not easy to think about this because the relation is not linear. If you increase the cache by a double, the effect you will see is not by a double, it's more, because of the way that real users in real world actually act. So by increasing the cache just a little bit, you can have a big impact on your system by having less requests come to your backend services. So I think it's really important to monitor everything, optimize something. There's this saying, like, premature optimization is the root of all evil. I completely agree. Also, the question that I get a lot is, since you're not on the cloud, what happens if your users exceed the current capacity, which is a totally legitimate question? Everything breaks. That's it. I'm kidding. So what we have is we have dedicated machines, and then we detect if the load on those machines is high, and then we just spin up virtual machines. They join the cluster, the loads get distributed, everything works. So it's kind of a hybrid cloud approach, where you get the benefit of really low-cost machines that are highly performant, more performant than on the cloud. And if you need extra capacity, you just spin up virtual machines, which cost more, but you run them for half a day, and that's it. So there's also this thing called the speed of light, and our data centers are in Europe. So for all of the other users outside of Europe, their latency is higher because, unfortunately, we have to deal with the speed of light, which usually you don't think about that. So I sent out an email to one of our users that's from Australia, and I asked him, can you please record a video of the app so that I can see how the app itself is performing to see if it's fast? He replied, sure, mate, the app is great, everything is working perfectly. I opened the video, and I got to see this screen. honest to God, I did not know we had loaders in the app. Because in Europe, where I'm from, it's really fast. You don't actually see the goddamn loader. And I was like, those poor guys, like this is normal for them because they're so far away. Everything is slow. And I had, OK, so we need to fix this because you can get an edge over your competition. So what we did, since the caching layer is separate, again, we could just spread out those machines. They can be anywhere. And we can do geo-routing to route them to the nearest one. So that's what we did. And the result was pretty amazing. So we reduced the latency in Australia from half a second, which you can perceive as a loader, to 80 milliseconds, which is basically instant. And we saw an increase in users in those areas. And this is all over the world, but I got the screenshot from Australia. And now, again, we are all engineers. You might ask yourself, shouldn't a CDN do this? Why are you doing this yourself? It should. We were using Cloudflare at that time. Now, when I created this presentation, I did not know that Fastly was a sponsor. OK? So that's a disclaimer. This is not sponsored in any way. So we were using Cloudflare. They have a problem with purging. So their purge doesn't work well. And also, you have a rate limit. So we cannot purge as much as we want to. So we had to build this ourselves and set a TTL on Cloudflare to just 3 seconds. And then like 4 or 5 months ago, we switched to Fastly, which actually has good purging mechanism. So we deleted all of that. But like, you can do it yourself, partly. Otherwise, if you use a good CDN, you don't have to build out yourself. You get that built in. Data centers can burn. I don't know if you know this, but like they can burn. Our data center provider, which we use to rent out servers, is called OVH. And this is an OVH building burning. Fortunately, this wasn't the data center we were in. But at that point in time, we were in just one data center. So if it happened to be the one that was burning, that would be a really fun couple of weeks for us to recover from. But that got me thinking. OK, so you cannot put all of your eggs into one basket. You have to have multiple DCs, multiple availabilities on whatever. You cannot just have one, because cloud can also burn. So in that point in time, we also switched to Kubernetes. Now, I think that Kubernetes is an amazing piece of technology. I really love it, and also hate it at the same time. Because I think we, as engineers, love trying out new stuff, and we love to jump on the hype train. And usually, you don't think about the consequences that this has. And my advice to anybody who's on the cloud, if you don't really need Kubernetes, you probably should think twice, because it's really hard to maintain once it gets out of hand. And also, if you don't have people who really know what's happening under the hood, when things break, and they will break, you're not going to have a great time. It's really difficult to know everything. It's really simple to do a POC. It works. Let's ship it. But then, like 2 years in, you might have some fun things to do. But we are running it on bare metal because we want to have the cloud-like capabilities even on bare metal, and that's what Kubernetes allows us to do, and it does that well. We crashed the cluster 3 or 4 times in the meantime. But yeah, now we know how it works, so that's fine. Also, if you're not on the cloud, it's difficult to do stateful applications. In the cloud, AWS does everything for you, right? It allocates an EBS, it attaches to your container. If your container dies, it will get attached to a different container. If you're on bare metal, this is the thing to use. So Longhorn is basically a distributed file system. Let's call it like that. It's not that, but it allows you to provision volumes, and it will be replicated across machines. The cool thing is we can replicate across data centers, which you cannot do on the cloud, unless you're using this. So if you have a container in one data center and that data center breaks, your data that was there will not be replicated to another data center. With this, it will. So I saw people using Longhorn in cloud just to have that possibility to migrate containers from one DC to another, from one availability zone to another. We also do a lot of real-time updates. And we first built out the system ourselves. We were using something in Node.js, which I forgot how it's called. Never mind. It didn't scale really well. And then we tried to rewrite it ourselves. It also didn't work real well. And then we found out a cool software that's basically a pub sub server. So that's all we wanted to do. We wanted to publish updates. We wanted to have our devices listen on those updates. And instead of fetching via REST all the time, you just want to subscribe to a topic. And then if a change happens, you can display the score right away. So it feels fast, so it feels instant. And there's this really cool software called Nats. It's under CNCF, free, open source, really high performance, low memory requirements, low CPU, that basically acts as a pub sub. All of our 28 million devices connect to the cluster, and they receive updates. And it's just a couple of machines. That's how efficient it is. So our peak was 835,000 active connections on 6 machines. And the capacity was under 20%. So we could have 4 times as much connections with the same setup. And we can also do in peaks, we do 500 messages per second. So I think I saw on some of the previous talks, like you can buy a pub sub server where you get 100 messages per second for $5,000. We do 5 times as much for $200 on dedicated machines. We also have a lot of data. We have more than 2 petabytes of data. So every time somebody does something in the app, it's sent to Firebase. It's anonymized. And then we download the data that's anonymized to analyze what's happening in the app and to optimize our app campaigns and see which features are working well, which aren't, and do all of the analytics. And if you're not on the cloud, it's difficult to store 2 petabytes of data, right? If you're on the cloud, you just use Google BigQuery or whatever, and it works. You pay for it, it works. But on bare metal, you cannot do that. So we use a software called ClickHouse. Again, free, open source. It can handle an amazing amount of data quite easily. So it can compress the data also. It's column-oriented data store that's basically a SQL database, but you don't do joins. And it compresses content. So those 2 petabytes are actually 50 terabytes on disk because of how good the compression is. And we have 1.4 trillion rows. I mean, we have more now. This was a couple of months ago. And we were importing some data, and I got this screenshot of 2.15 million rows per second of import that was going over the course of 48 hours, so it can handle a lot. We also have some really interesting peaks. This is a screenshot from Google Analytics, which shows, they used to call this real time. It's not real time, it's in the span of 30 minutes. But you can see almost 2 million people are active in that span of time and are actually browsing the app. So we have really big peaks. And the reason why we are doing this, all of these things without the cloud is because our infra cost is 0.6% of the revenue. And it keeps getting lower every year because our revenue grows and our cost doesn't grow as much. Because if you have a good system, especially if it's on bare metal, machines get cheaper over time. So basically, our costs keep getting down. I think the next year, we predict that it's going to be 0.5. I guess in 5 years, it's going to be 0%. I don't know. So to finish things off, cache all the things. People usually tell me, yeah, but I have an app that's personalized, You cannot cache personalization? Yes, you can. We have personalization in the app. You can do it. You just have to know how to design your API, and there are a couple of tricks. If you have those issues, you can always reach out. I love to talk about this, but you can absolutely do it. Be stateless wherever possible, because that's the way to scale. Know how your users interact with the app and try to model your system so that it fits better with how your users use the app. Recognize the right tool for the job and change if necessary. Cloud should be the default. I strongly believe it's an amazing technology that we have today that we didn't have before. It should be the default for all of the apps, but maybe for some of you, sometimes, in some case, it might be better to move away. I see a lot of companies moving away that have really big AWS bills. Queue everything that is slow, and remember that this technology is working perfectly. Monitor everything, optimize something. Don't do it before it's actually necessary. And keep it simple for as long as you can. Because if you complicate your system before it's actually needed, you get stuck on trying to implement the system instead of focusing on the business, and business is what gives you your revenue. That's it. Thank you.
Yeah, excellent talk. I love this talk, so it's my topic, so thank you. Yeah, I think you answered some of this, but you mentioned how big the Postgre cluster was, right? In the
No, so that was...
okay, sorry. So they were asking, like, how big is the Postgre database or cluster to support this load?
Yeah, so the things I was showing was about ClickHouse, that's 2 petabytes. And Postgres is not actually that big.
Sorry, guys, like...
The database itself, we try to keep it as lean as possible and optimize regularly. So we have one master and one replica. And the data set is actually not that large. It's just 250 gigabytes.
OK.
So it fits, the whole data set fits into memory.
Yeah, I was going to say that.
So it's really fast.
Yeah. So it's essentially you rely on the Postgre cache, no? To like.
Yeah.
Okay, so someone is, well, not someone, like people like, some people are arguing that you somehow ended up building a small version of a cloud. I would argue that, but yeah.
Yeah, not really, because, I mean, we use Kubernetes to get the cloud-like capabilities. That is true, and that's why we use it. But we didn't have to build out from the scratch. We use existing technology, but you get really big savings. Again, like for us, it makes sense because if that wasn't the case, we couldn't have the cost that we have now. So we can switch to the cloud. That would be great, but the cost would be like 20x more.
Yeah. So did you recently have to do a full cold start or never, like from zero?
No. So
Okay.
we had a thing where one of the data centers went offline, but then like everything switched to the other, and the capacity grew because the auto-scaling with the virtual machines kicked in, and it worked. But yeah, we didn't have to do a cold start, but everything is automated. So all of our machines are provisioned with Ansible. All of the code is in Ansible, and everything else is in Kubernetes. And we try to do all high-performance stuff outside of Kubernetes. So Varnish, Postgres, ClickHouse, NATS, everything that's high-performance is outside of Kubernetes on the bare metal.
Okay. So they're asking about how does observability look at that scale, and in terms of like logging and tracing, how do you choose? Because like, do you log trace everything? Probably not, no?
Oh yeah, that's a good question. Yeah, we have a lot of logs. So we import all of the logs from Fastly, and that's 400 billion rows every month. And we analyze that, and we also do we do bot detection and anti-scraping with that, which is basically just SQL from ClickHouse. We log all of the queries that update the state in the database. We do that in Logstash, and that's a lot of queries, because we want to be able to debug. And we also log everything that's, I mean, obviously all of the errors, but when an error happens, we have all of the stack trace and all of the logs that came before. so you can debug that error. But yeah, we have a lot of logs. The stack itself is pretty standard. So we have Influx, we have Grafana, we have Telegraph, and for HTTP logs we use ClickHouse because that's the only thing that can actually store the amount of data that we have.
So in terms of Varnish, is it the open source or you're using some enterprise functions?
Open source.
Open
source is enough for everybody.
Okay, and then yeah, they're asking if you use priority queues or something.
No, there's no need because there's enough capacity to handle everything. But we do have the capability to turn off parts of the system gracefully if we get to a point where, due to unforeseen circumstances, like the load was too big and we are unable to scale, we can just shut down the parts of the system that we want that are maybe causing the issue without actually having an issue on the other part.
Mm-hmm. And then finally, we discussed that inside, but they're asking if you're using a PHP framework and which one.
Yeah.
We all know the answer, but
I mean, so usually people are surprised, like, why PHP? Like, because the developer experience is really great. You can focus on business without actually having to choose the technology. What we have is Symfony. So the latest PHP with Symfony and our own open source library to detect what's changed, and then we know how to purge it. And basically, PHP is simple because like every 5,000 requests, the workers is just restarted, so you don't have memory leaks. It works perfectly, and it's really I mean, that's how you fix
them,
stuff.
but
Yeah.
they disappear, no?
Yeah, and it allows us to focus on business and to have a really good cache.
All right. Thank you very much.
Thank you.
Thanks a lot, Josip.